All right, let's go and get started. So the plan for the day is to finish up this module that we've been looking at for the last few lectures on localization and mapping. And just to remind you of where we are so far. So in the last two lectures, we've been looking at applications of base filtering to the problem of localization. So localization is the problem of figuring out or estimating the robot's location given a map of the environment. And we did this 2 lectures ago, so I think this was lecture 14, I believe, where we did localization. And in the previous lecture, we considered the problem of mapping. So estimate map of the environment and if you look back to the previous lecture, for the mapping part, we assumed that the robot had some way to localize itself in some kind of global reference frame, and all it's doing is figuring out the map of the environment. And I guess along the way we discussed different kinds of maps, so location-based maps, feature-based maps. For the most part, we've been working with occupancy grid maps. I guess those are relatively kind of conceptually simple, and a lot of the algorithms we've discussed also apply to other kinds of maps. So yeah, I guess if you think about this, neither is completely satisfactory, right? So localization, we were assuming that we had a map of the environment. Mapping, we're assuming that the robot can somehow localize itself. In practice, what you'd like to do is just deploy a robot in some new environment and do both of these things simultaneously, right? So the robot should be able to figure out its location, maybe in some reference frame, and also as it's moving around, it should be able to build a map of its environment. So that's what we're gonna do in today's lecture. So this goes by the name of simultaneous localization and mapping. Usually abbreviated as SLAM. And I guess what we're going to do is kind of put these two components together in a way that we'll get into to jointly estimate. Let me just write it here. So the problem of doing SLAM is to jointly estimate the robot's location and a map of the environment. Okay, and I guess just as a quick caveat, so there's a massive amount of work over, I guess, multiple decades on the problem of SLAM. We're not going to do any kind of justice to this large literature. Yeah, even nowadays, like people still write like lots of papers on SLAM. We're going to look at just one particular approach called grid-based FastSLAM. So the grid-based part comes from the fact that we're going to be looking at occupancy grid. That's going to be our map representation. The fast part, I guess it was fast when it was first introduced, which was some time ago now, maybe like 20 years or so ago. But yeah, I think this is a decent like starting point for SLAM. So I guess without any kind of further knowledge, if you just want to implement something from scratch, this is a decent place to start, and there's a whole bunch of like bells and whistles that people have developed over the years, like I said. So I guess before going into the the algorithm description, let me just say a little bit more about SLAM. So this is chapter 10 in the probabilistic robotics book. And it's useful to consider two versions of the problem. So two versions of SLAM. The first version is what's known as online SLAM. So the problem in online SLAM is to estimate some, I guess, probability distribution over the instantaneous location and map. So basically, at every point in time, as the robot operates, as it moves around in some environment, the only thing that it cares about maintaining is where is it at that point in time, so a belief over its location, and a belief over the map at that instant in time. So this is in contrast to the other kind of version of the problem, which goes by the name of full SLAM. Where the goal is to estimate, again, some probability distribution over the entire trajectory. So trajectory of visited locations, and also a map. So I guess pictorially, let's say this is the online version. So we just have some map of the environment, some obstacles, and an estimate of the location. So really, you should think of distributions over the map, distributions over the location. With the full SLAM version of the problem, what you're doing is maintaining a distribution over the entire trajectory. So maybe you started off here, and then you're here at time t. So you have a distribution over trajectories that you visited. So the full SLAM version is kind of harder than the online SLAM version in the sense that you're trying to do more, right? You're trying to estimate not just where you are at the current time step, but you're also trying to estimate where you've been at previous time steps. In some sense, I guess you could use, so if you were able to do online SLAM, you could use that to get an estimate for full SLAM just by, like at every time step you maintain a belief, and you just concatenate those beliefs together, and that gives you a belief over the entire trajectory. But with full SLAM, you could do a bit more. So if you get a little bit of extra information, if you get some new information at time t, you could kind of refine your estimate of where you were previously. So which version of the problem you look at kind of depends on the context. Maybe I can pose this as a question. I guess does someone see, or yeah, go ahead.
I was going to ask, what are the practical applications of knowing where you did?
Yeah, okay, well I guess I was going to ask that as a question. So yeah, can you think of practical applications of knowing where you've been? When might you use it for a robotics application? Go ahead.
If you're like a leader robot and like follower robots need to follow like road path, then it's kind of useful to know like, oh, this is a path for sure that works.
Yeah, that's reasonable. Other thoughts? Go ahead.
Do you know your position at certain nodes of a trajectory, and could you fill in what was happening at the interim?
Yeah, yeah, you could. That's reasonable as well. I guess the one I had in mind was some kind of like search and rescue mission. So if you're deploying a robot in some like disaster-stricken like area, let's say, and you're trying to find someone, then something you want to do is like coverage, right? So you want to make sure that you've covered the environment and you've, yeah, if there's like someone who's kind of stuck in some part of the environment, then you haven't missed them. So to figure out whether you've covered the environment, it's like useful to know where you've been. If you know where you've been, then you can decide like whether or not you've covered the environment. Question?
How much more accurate is like the full SLAM than like just concatenating your previous delete?
Yeah, so it can be more accurate to do the full SLAM version. We'll get to that later in the lecture. I'll show you some specific instances where doing like full SLAM can like get you more accurate estimates than just doing online SLAM. Yeah, I'll show some examples.
And then would you ever like kind of use the full SLAM to go like back, and now that you know that you have like a kind of higher certainty that you were in fact at a certain location, can that inform like where you currently are? Like, will you ever use the information as a kind of the other way?
I'm not sure I followed. Like to go back.
Like, so you can use the information to go back and see like your trajectory, but then now that you have a better idea of what your trajectory was, could you use that information to better inform?
Oh, I see. Yes, yeah. So you could do this kind of like iteratively. So I guess full SLAM doesn't say that you need to do it that way, but that could be one way of doing it. Like you refine your estimate of where you have been, and then you kind of go forward in time. So you do these like forward, like backward passes. That's one way you could do it. Yeah, there might be like other ways you could do try to tackle the full SLAM problem as well. Okay, so I guess what I'll focus on today is the online version of the problem. I won't say too much about the full SLAM problem. If you're interested, basically like a similar kind of technique that I'll describe today that can be applied to the full SLAM problem. That version is described in the book if you're curious. But yeah, I'll focus just for simplicity on the online SLAM problem. So like I said, the specific technique that we're going to discuss is called grid-based FastSLAM. So this is chapter 13.10 in the probabilistic robotics book. And the basic idea is actually going to be fairly straightforward. We've done all the hard work in the past two lectures where we thought about localization given a map and mapping given localization. So the basic idea is to combine the particle filtering approach to localization so that was lecture 14, 2 lectures ago, with occupancy grid mapping. Which was the previous lecture, was lecture 15. So that's I guess the high level approach. So I mentioned we're going to be doing particle filtering. So I guess similar to when we looked at particle filtering for localization. So for localization, the picture was, well, I guess we were assuming that we have some map of the environment, so we know what the obstacles look like. And the particle filter maintains this approximate belief, this approximate like distribution over its the robot's possible locations in the form of a set of particles. So the robot is very confident of where it is, then the particles are kind of close together. Maybe there's some floating particles elsewhere. So that's the representation for localization. Let me just write it here. For mapping, in the previous lecture, I guess this is slightly harder to draw, but we were maintaining a belief over maps, right? And the way we did that with an occupancy grid map in the previous lecture was that we had some probability associated with each cell being occupied or not, and then we updated those probabilities as the robot moved around and collected more measurements. So with SLAM, what we're going to do with this like specific approach, like this grid-based FastSLAM, is maintain a set of particles where each particle actually has two things associated with it. So one is a candidate location, and a second is a map. So you can think of a particular location and a particular map as corresponding to a particle. Like that's one particular hypothesis about the robot's location and about the map. And in this particle filtering approach to SLAM, we're going to maintain a whole bunch of these pairs. So I think maybe it's easier to visualize this with a picture. So, all right, here's a so here's one particular, let me draw a few of these. How many did I draw? One, two, one more. Okay, so these are meant to represent particles. So let's say there's, this is particle 1, this is particle 2, and this is up to particle capital M. Capital M, again, if you think of it as just some large number, 1,000, 10,000, million, whatever really fits on your computer. And each particle, as I was saying here, corresponds to two things. One is a location, the other is a map. So here's one, I guess, possibility. So this is what the map looks like. So these cells are occupied. And let's say this is a candidate location. So the crossover here. So maybe the way to think about this is that this is the robot's location, marked with the X, and like the occupancy kind of map here represents one particular map. So this is one specific hypothesis, right? So one like point kind of estimate about the robot's location and the map. So with the particle filter, we're maintaining, or we're going to maintain a bunch of these. So let's say this is the location estimate. So this is another particle corresponding to a particular location and a particular map, and so on. We're going to have capital M of these pairs pairs of location and map. Question?
And it's like a particle in the sense that it's just like a vector of values where like each value can, where each value denotes like whether it's occupied or not, and then where it's physical.
Yeah, so I think intuitively the way to think about this is that we're trying to represent a joint distribution over the location and the map. So that joint distribution is some extremely complicated like object that's like very high dimensional, right? So it has dimension equal to the robot's like location dimension plus how many ever like cells you have in your grid. So it's a very high dimensional space that we're trying to represent a distribution over. But we're doing this approximately via particles, and yeah, each particle is one particular like instantiation of a location and a map. Yep, does that make sense? Okay, good. Yeah, so I think this is really the main idea I want to convey. I feel like if you get this, the rest follows relatively straightforwardly. So if you have questions on this, I'm happy to try to answer. Okay. All right, so let me switch to the slides, I think. Okay, so another picture, same concept as what I was trying to represent before. These are three different particles. Each particle corresponds to a particular hypothesis, just 1 point estimate of the location. So that's the green circle, and one particular hypothesis about the map that's represented by these three pictures. So I guess what you would hope is that if you're very confident about the location and the map, then all the particles look kind of the same. So all the particles have roughly the same location and roughly the same kind of looking map. If you're uncertain, then maybe the particles and the maps are going to look very different from each other. But yeah, the point is that we're going to maintain some large number of these, capital M of these, and we're going to update them as the robot moves around and as it collects more sensor measurements. Okay, so here's the algorithm for grid-based FastSLAM. Let me just go through the structure of it, and then I'll describe each function a bit more carefully. So this has the structure of a particle filter. I guess hopefully you're familiar with the structure of the particle filter. So at each time step, we're going to do a bunch of steps for each particle. So in the first for loop, K is indexing the different particles. So we're looping over the different particles indexed from 1 to capital M. Yeah, I'll go through the functions a bit more carefully, but roughly what they're doing is some kind of dynamics update. So if you have knowledge of the dynamics of the robot, and it's also updating a map. So that relies on the technique we discussed in the previous lecture. And the WT, so that's importance weight, that showed up also when we were looking at particle filtering for localization, which roughly corresponds to how likely is the sensor measurement given a location and a map. Yeah, I'll describe all of those in more detail. So that's the first loop. You can think of it as basically doing a dynamics update and calculating these like importance weights W. And then the second for loop is doing the resampling step in the particle filter. So for K equal to 1 through M, we're drawing index I with a probability that's proportional to WT. So WT was high, let's say like 0.9, then we sample index I with probability proportional to 0.9. Yeah, and then we just keep sampling capital M times and then add the location xt and the map mt. So that particle consisting of the pair of location and map, we add that to st. So okay, I guess the last part is identical to particle filtering as we saw it before when we applied it to localization or state estimation more broadly. The only distinction here is that the particles contain more information. So previously, a particle was an estimate of the location. Here, a particle is location and map. But the last for loop is identical to what we had seen before. I guess questions on the general structure before I describe the details. Go ahead.
So how does it update the map? Is it also using sensors or arrays, or what does it do?
Updating the map. Yeah, so roughly it's what we were doing. Actually, it's using the technique from the previous lecture. So yeah, let's go through the different functions. Maybe I can just write it here instead of putting the projector up again. So yeah, I guess let's go through each of the three functions. So the first one is the sample. Can everyone see when I write here? I think you should be able to. Maybe raise your hand if you can't see. Okay, good. All right. So sample motion model. So what this is doing is the dynamics update, which we discussed kind of versions of or ways to implement it 2 lectures ago when we were thinking about localization given a map. So what this is doing is sampling x t k. So k again is indexing the particle. So we're sampling a state at time step t from the conditional probability distribution xt given x t minus 1. So that's the previous state, the previous control input. This is k.
Sorry, can you please turn on the lights on the front?
Oh yeah, sure.
Thank you.
Okay, good, thank you. All right, yeah, so we're sampling xtk from this conditional distribution. So this is our dynamics model, and then there's a map mt minus 1 k. Yeah, so given a location or a state at the previous time step, given the control input that the robot took, which it knows, and given its previous estimate of the map, given some estimate of the map as captured by particle k, we're sampling some possible next state for the robot. So yeah, if you understand the dynamics of the system, this is like capturing that, like just sampling from that dynamics model, which potentially could be probabilistic. Yeah, I guess we had discussed like different ways of doing this a couple of lectures ago, where you ignore the map, you ask yourself what would the robot have done if there were no obstacles, and then you take into account the fact that some of the portions of the environment are occupied. All right, any questions on this function? Okay, so let's discuss the second one. So the updating the occupancy. Let's do it here again. Updating the occupancy grid map. So mt k. Actually, let me not write this. What do I call it? Updated. Occupancy grid map. So this is taking in as input the current sensor measurement. And typically for these kinds of applications, you have some range sensor, so some like distance sensor, something that gives you distances to different points in the environment. It also takes in this updated location estimate, so updated after you sample from the motion model, and the previous estimate of the map. So the way this is implemented, or the way this could be implemented, I guess there's many ways of doing this. But one way, the default way in this algorithm, is to use the occupancy grid mapping from the previous lecture. And yeah, I guess one way to do that is to think about this map, like MP minus 1K. So the map estimate from the previous time step as corresponding to a prior. And then we can use the occupancy grid mapping kind of update of the beliefs that we described in the previous lecture, where you take the prior over maps and then you incorporate the sensor measurement that you just received at time step t, which could be noisy, and then you incorporate this location xt. So I guess what we're doing here is that we're assuming, so we're applying the technique from the previous lecture, the occupancy grid map technique, but assuming that the location is correct. So we're kind of alternating. Like we're first assuming that the map is correct, and then updating the location, and then we're assuming that the location is correct, and then updating the map, or a belief on the map. And so this is kind of like a general strategy that shows up not just in SLAM, but many other like areas as well. Like often, like problems have the structure where you can figure out A given B, and then you can figure out B given A. But what you want to do is like jointly estimate A and B. So yeah, the trick is to kind of alternate between those two algorithms. Like you first assume that B is correct using some initialization, estimate A, and then assume A is correct and get B, and you hope that that converges. This is not like globally like optimal in any sense, but it often seems to work reasonably well. Question?
Do we have to know the potential like size of the map before we start this?
Yeah, good question. So we're assuming that we've like committed to some size of the map, and I guess size could mean two different things. Like size could be like the spatial like extent of the environment, or the number of cells you're considering. Yeah, in this algorithm, we're assuming that both are like you've committed to some size and some like resolution for the discretization of the map.
And one more follow-up.
Yeah.
Just when we're updating the map, are we like adding new values to some map like variable, or are things set to like null or 0 or something, and then we're updating that?
So okay, so I guess I didn't say how to initialize this, but you can assume that you had. So in the previous lecture, what we did was we assumed that we had some prior over maps, and the prior was pretty simple, right? Like each, like the way you draw a sample from that prior over maps is you look at each cell and then you just do a coin flip, a biased coin flip. We said like the probability of a cell being occupied is something like 0.2 or 0.3. So you can do that before you initialize this. So you have a bunch of samples where each sampled map comes from that prior. And then you also assume that you have some prior over locations. And that's how you initialize the set of particles before the robot like does anything, like before the robot gets any measurements. Question?
Do we have it baked in where impossible things aren't taken at each time step? For example, something being localized where it also thinks there's an obstacle.
Okay, yeah. So yeah, good question. So that's where actually the third function comes in. So the third function estimates a likelihood. So WT K. So for each of these particles, we are evaluating the measurement model. So this is taking in 3 arguments again. So ZT, that's the current sensor measurement, XT, K, that's our best estimate right now of the location, and then MT, K, which is our best estimate right now of the map. And what this step is doing is computing the likelihood. So P of ZT, so the likelihood of receiving the sensor measurement that the robot received right now, given the location and the map. So this is the measurement model which we're assuming that we know, and we discussed kind of versions of if you have a range sensor a couple of lectures ago. So I think ideally this step is the one that should like filter out things that are not likely, right? Like not feasible, not consistent. So if you're in some location xt and your map is this, and these are inconsistent in the sense that you said, like where your location is like inside some obstacle, then like given that that's not actually possible, the likelihood of receiving the sensor measurement that the robot received like should be very low or zero. So when you do the resampling step, the probability that this pair of location and map gets sampled, that probability should be very low or zero. Ideally it should be zero, right? If it's like truly inconsistent, then you should just like not like sample this when you do the resampling. So the weight over here should be either very small or zero, and so when you resample, you're not going to get that. You're going to filter that away. Question?
Can this model account for like a moving the dynamic map?
Yeah, that's a good question. So the way I described it, so that general structure should still be like valid. The extra thing you're going to have to do is like have a dynamics model on the map. So it could be that the map is not just like static obstacles, maybe there's like humans as part of the environment that you're thinking of as like being part of the map. If you have like some dynamics model for the map itself, then you can basically modify each of these like functions to take that into account as well. It's a bit more complicated, but actually like practically like very useful, because often like things do move around and you need to account for that. Yeah. But yeah, I guess going through that might take a bit of time, but that's the rough idea. Like if you had some way of sampling how the map can change, then you can like consider variations of these functions. Good. Other questions? All right. Okay, so that's that's the basic algorithm. Maybe just one more question. So in practice, I guess what do we use maps for? So one application of mapping or SLAM could just be that you literally just want to build a map of some environment, right? Like you want to go in somewhere, you want to figure out what the environment looks like. Often what you want to do is planning. So you want to use the robot's kind of updated information about what the environment looks like to plan a path for the robot to get to some location or to cover the environment or so on. So I guess how can people think of like ways of using this like particle filtering based approach to SLAM for doing planning as well? Maybe simple ways or more sophisticated ways. All right, I guess here's maybe a relatively simple way. So at the end of this process, like at time step t, we have capital M particles, and each of them have some kind of likelihood associated with them. Like that's the WT. So we can just do maximum likelihood estimation. So you just pick the location in the map that has the maximum likelihood, and you treat that as the ground truth, right? So you just say, okay, I'm going to commit to this like particular like hypothesis, and I'll plan some like path using all the different like techniques that we discussed, like breadth first search, A star, Dijkstra, all of that, or other like algorithms, given that specific like hypothesis for the location in the map. So that's I guess reasonable. I guess can you think of problems with that or like change like variations of that to make it more sophisticated? We actually have like more information than just a particular estimate, right? Like we have some like notion of like uncertainty. Go ahead.
you wanted to, you could actually make multiple plans
Yeah.
for respective particles, and you can sort of take, you can see the distribution of actions that you might want to take, or plans that you might take, and then take a plan based on that distribution.
Yeah. Okay. So I guess you can. Right. I see. So for each of these, each of the particles, you can make a plan, and then you can see like what's the action, like the control input that.
Yeah. So like if we have one particle that we're very confident about, and based on that we want to go left.
Yeah.
But we have many other particles that are maybe just a little bit less probable, but
Yeah.
we have tons of them, and they say we should go right.
Yeah.
Likely we want to go right. Just
Yeah.
because the consistency in the plans of the individual particles.
Yeah, yeah, I think that makes sense. There's I guess a variant of that where you find a single plan and then you evaluate the expected value, let's say, of collisions given these particles. So for each, so let's say I have a particular plan and I want to evaluate some like estimate that plan leads to a collision. What I can do is look at that plan for every particle from 1 through m, given this like set of particles that we have, and then we just look at the weighted like sum weighted by the WT, and that gives us like some estimate of whether a particular plan is going to lead to a collision or not, and then we find some plan that minimizes that expected value of collisions, and then maybe maximizes some probability of like getting to the goal. So that's another way as well. That's a bit, well, yeah, I guess these are kind of more computationally intensive because you have to find a plan that works like in expectation over all these particles, and you have to evaluate the plan for each of the different maps. If you have a lot of maps, then that could be computationally intensive. But the good thing is, I guess a lot of these things are parallelizable. Like you can evaluate a plan across different maps completely in parallel. And if you have like multiple like cores on your CPU then or GPU, that's something that could be efficient. But anyways, I guess that's just to give you a flavor of the kinds of things you could do with this. So this is giving you not just a particular map in a particular location, it's giving you some estimate of like uncertainty as well. And often like planning algorithms can benefit from that kind of uncertainty estimation. All right, let me switch back to the slides. Okay, so this is grid-based FastSLAM, like working in practice. Yeah, I'll show you more sophisticated videos, but this one has a particular thing that I want to point out. So I'm using this. Yes, this is a laptop on a. So yeah, the laptop is kind of going around. It has a range sensor, and let me see. The left is the estimate, like the best estimate basically for what the location and the map is. Again, like what we really have is more than that, right? It's not just one particular location, one particular map. We have a bunch of particles. What's being visualized is just the most likely location and particle. So the robot goes around this kind of corridor-like environment. What's on the right is the instantaneous measurement that the robot is getting. So instantaneously, its range sensor is giving it some information about occupancy just around its current location. But the plot on the left is the SLAM part.
Is the most likely based on the weight?
Yeah, just based on the weight. So the largest weight. Yeah, exactly. Yeah, what's interesting, so we'll come to it in just a few seconds. So you can see the error that it's making where, well, we can guess that it's error. No building looks like that, right? So the corridors are not kind of perpendicular to each other. And yeah, I guess the next portion is the interesting thing. Okay, yeah, right there. So let me just play that again. So So yeah, just keep an eye on the plot on the left. Yeah, does someone see what happened there and maybe have a hypothesis? Go ahead.
You have a lot of particles that have a particular guess of what the sort of upper right L
Yeah.
looks like, and some of them are correct, but maybe they're not the most likely ones, or like they don't have the highest weight. So what we visualize, at least, the best guess we have is some awkward angle.
Yeah.
But we still have some like particles that guess that we have the correct
Yes.
angle just in the background. And
Yeah.
once we get new information that basically brings our belief more in line with the
Yep.
other ones, that's when it sort of shifts.
Yeah, that's exactly right. And I guess the specific thing that's happening is that the robot is like coming back to a location that it's visited before. And that kind of makes the map like snap, well, the most likely map, like snap the corridor into a shape that's actually correct. So this like process is called loop closure in the SLAM literature. So as the map is being constructed, there may be errors that accumulate. So this is another example where obviously the corridor isn't actually at this like weird angle from the portion of the building on the left. But yeah, as the robot like moves around, like it goes far through the corridor, kind of loops around, and then comes back close to some location that it's been at before. So if the robot comes back to a location that it's previously visited, then it can kind of like correct, just like automatically, like through this particle filtering process, like correct these like large errors in the map. So this process is called loop closure because you're kind of like closing the loop, like you're coming back to some location that you visited before, and that helps you update the estimate that you have for the map and your location as well. But it's basically because you have some particles that are representing like the true like map, and those become more likely when you receive some like new sensor information, like when you come back to a previously visited location. So this is showing, I guess, before loop closure and after loop closure. So before loop closure, the corridor is at some like weird kind of angle. Once the robot gets back to some location it's visited before, what happens is that the corridor kind of snaps into place, becomes perpendicular, like as you would expect from a real building. So yeah, I guess FastSLAM kind of automatically does this loop closure. Like the intuition is that the particle corresponding to the correct map will have a higher importance weight once you get this new information from the sensor when you get back to a previously visited location. But yeah, I guess for this to happen, you need a sufficiently large number of particles because you need like some particles to represent the truth. I guess if you have like no particles that represent the truth, then yeah, you've kind of completely lost like touch of reality, and you're not gonna like come back and like get the true kind of like correct like estimate for what the map looks like. Yeah, and just I guess as a reminder, the particle filtering is like throwing away particles with low importance weight when we're doing the resampling step. So if you don't maintain enough particles, like it could be that you somehow like lose the particles that like correspond to the actual like ground truth map. Question?
Yeah, how common is it to do, like, is it, like, basically how common is it to do a loop closure and have the incorrect conclusion?
Yeah, it's fairly common. Like before the loop closure step, like it's pretty common that you'll see like these weird kinds of maps that don't make sense. But like after you come back to the same location, like those errors like get corrected. Yeah, and I guess I mentioned this already. So maybe this addresses your question as well. So as the time between like closing the loop gets larger, your like errors can like accumulate over time, and so you can end up with like more and more like kind of wacky looking maps. One interesting option that was like suggested in this paper is to do some kind of like active loop closure. So you try to actively promote loop closure by visiting locations that you've previously visited. So you go somewhere and you kind of backtrack a bit, and then go somewhere, backtrack a bit. So you don't let like errors accumulate over long periods of time. Does that address your question?
Yeah, I was gonna ask him like, are there like instances where like you're more likely to like think you were visiting somewhere, but you're actually not, like you're actually in a new location, but you think you're like, visiting somewhere?
Yes, so that is also possible. So if you have locations in the environment that look very similar, that could potentially mess you up quite a bit, right? So you could think like maybe you're visiting some previously visited location, but really it's just some other place that looks very similar, and that can mess this up. Then you get like pretty bad looking maps. Yeah. Yeah. So I guess I just like very briefly touched on this loop closure phenomenon. So there's a massive amount of work like in the SLAM literature specifically addressing loop closure. Like beyond just the kind of loop closure that happens automatically with this grid-based FastSLAM. There's a lot of techniques for doing loop closure using feature-based maps. So we're going to talk about computer vision starting from the next lecture. But basically, if you can recognize that you're visiting some previously visited location, so if like the visual features in the environment look pretty similar, even if the exact viewpoint is not the same, you can kind of do this like feature correspondence. You can look at portions of the image and correspond them to portions of a current image, correspond them to portions of a previously visited image. You can use that kind of information as well to help loop closure. I won't go into the details on this. I guess the point is just to like tell you that this is an interesting phenomenon, and there's many different ways of doing loop closure beyond the loop closure that comes out automatically of the particle filtering approach. All right, questions on that? Go ahead, Mike.
I guess like when you also have map in your particle, I guess it means like the convention of the particle goes like pretty.
Yes. Yeah.
That means you have to have like a lot more particles than when you don't have.
Yeah, that's a good question. So this does require a large number of particles because the space over which you're like representing the probability distribution, like the belief, is like not just the location but also the map. And so you want to make sure that you have like good coverage of that distribution. Partly it depends on the quality of the sensor. So if your sensor is very good, then you can like often get away with not like a ridiculous number of particles. If your sensor is pretty bad, then you're relying on like your dynamics model and the noisy sensor measurements, and so you might have like just fundamentally you might have a belief that's pretty like diffuse. If you have a good sensor, then like all your particles should roughly be like concentrated around the correct map. And then you don't like lose that as you kind of move like forward in time. So yeah, I think good sensors can help quite a bit, and yeah, but in general, if you don't, then you need quite a large number of particles. Another question?
This is going back a little bit, but for the measurement model, where we get the probability of sensing it based on FastSLAM.
Yes.
In the past, we've been given like those probabilities, right?
Yeah.
So how do we get it here?
Yeah, so this depends on the sensor. So I think maybe 2 lectures ago we had discussed one particular sensor. So this was a range sensor, and we discussed like a particular like probability model, like measurement model for the range sensor, which takes into account I think it was like 3 or 4 different factors. Like one is the actual like distance to an obstacle. The other is the probability that you miss an obstacle. The other one was the probability that you see a kind of obstacle that wasn't there. And then I think the fourth one was just like some random noise. And then we concatenated those probabilities together. So that's one way, or that's one particular sensor model. So if your robot has a range sensor, you can characterize like those error probabilities, like the probability that your range sensor sees an obstacle that's not there, and the other probabilities, and get a measurement model that way. So in the algorithm that I described, we're assuming that this is given to us. In practice, of course, it's not like we would have to go and do a bunch of experiments on our particular sensor to come up with a probabilistic model corresponding to the measurement model, and then plug that into the particle filtering algorithm. Yep. Good. Other questions? Okay, so I guess let's look at some more sophisticated implementations. So this is from the GRASP lab at UPenn. This was from a few years ago where, they're doing SLAM indoors. So the right is the third-person view. Top right is the first-person view, so there's a camera on the drone, and the video on the left is showing the map that the robot is building as it goes along. So as it's exploring this environment, I think here it's actually operating autonomously, I believe. So it's doing some path planning to explore previously unexplored regions of the space, and as it's doing this exploration, it's building up a map of the environment, and it's localizing itself within that map, and that's what's being shown on the left. One thing to keep in mind is that if you see drone videos indoors, these are GPS denied environments. GPS denied as in you don't have good GPS localization, and so the localization challenge is harder. Outside, so over here, for instance, you can get a decent GPS signal, and so you can localize yourself pretty well. But as soon as you get indoors, I guess you can try this with drones that have GPS. The GPS estimate just gets completely wacky, and you should basically mostly throw it away. This is a commercial implementation with Skydio. This was the company I mentioned a couple of times. They make these aerial photography drones. Let me just play the video. The audio actually explains a little bit about their SLAM.
Our initial focus has been to deliver on that promise of the autonomous flying camera and to make it real. Basically to create a film crew that fits in your backpack. It's a camera that understands the scene it's looking at and has the ability to move itself. Those two things together are just enormously powerful. This is a very ambitious product, and to make it possible, we had to develop custom hardware. We built a device with 13 cameras that see in every direction, and at its core, it uses an NVIDIA TX1. It's the same thing that's found in self-driving cars, and that's what runs the Skydio autonomy engine. The first step in the vision processing pipeline is understanding where the vehicle is and how it's moving. To do this, we look for regions of high texture in the environment, and we track those as landmarks in the real world that we can triangulate and track our motion. That motion estimate is the foundation for everything else we do. The next step in the processing pipeline is building up a 3D understanding of the world. To do that, we compute stereo depth maps from each pair of cameras, and these get fused over time into a dense 3D understanding of the environment.
All right, so I guess that last part, you can kind of see the representation that they're using. So it looks like an occupancy grid map, right? It's a bunch of voxels that's representing the map. They're doing a bit more, I guess, with computer vision and some of the stuff they mentioned with tracking landmarks and so on. We'll get to in a couple of lectures. The sensors they're using here are stereo, depth cameras, or stereo cameras that give you depth. So it's a kind of range sensor. It's not a LiDAR, but just depth estimation with multiple cameras. They actually have 13 cameras. I believe the 13th camera is the high definition, the camera that's tracking, that's capturing the footage of whoever, this biker, for instance. The other 12 cameras are for doing mapping and obstacle detection and so on. Okay, questions on that? All right, so I guess the last thing I want to talk about, so like I said, this is the last lecture on SLAM. I just want to zoom out a bit, and I feel we often think a lot about the really technical aspects of these things. It's important, I think, to zoom out from time to time and just think about some of the broader societal implications of these technologies. We did that a bit when we thought about like optimal planning and optimal control with the value alignment problem. Like how do we make sure that some objective function, some cost function that we program onto a robot like actually reflects our like human values. I think the interesting thing here has to do with like privacy. So SLAM, like mapping and localization, is obviously a really powerful technology with lots and lots of different applications, self-driving cars, drones, and so on. But yeah, I think there's an important question about privacy. So I guess what happens if you have like millions of robots that are like deployed across many different homes? You might think this is far-fetched, maybe. Like, are we really going to have like millions of robots across people's homes doing SLAM? Turns out we already do, and we have had them for a long time. This is an article from 2015, I think, so like 7 years ago, where the iRobot Roomba, like the robot vacuum cleaner, they use vSLAM. The V is just like visual, so SLAM based on vision for like mapping out like an indoor environment that you want to vacuum up. So yeah, I think there's probably like room for technical solutions. So maybe there's some way for the robot to still do what it needs to do, like clean an environment, but then not building a map or somehow building just enough of a map to do what it needs to do. So not build like a full kind of like detailed map of the environment, or like not track humans in the environment. That's the other thing. But it's probably not just a purely technical question. There's some societal questions as well. Yeah, thoughts or questions?
If the robot never shares the information with like iRobot or anything like that, then what's the point of it having their detailed map?
Yeah, so maybe just to repeat the question, if the robot doesn't actually share the information, maybe just like builds the map locally and doesn't share the information, what's the problem? I guess, I don't know, do people have thoughts? Like, is there still a problem, or is that fine? In some sense, it seems like it's fine, right? Like we have these robots, and no one is complaining that much. Go ahead.
As long as that robot isn't shared with other people, then it would be fine. As long as there's like, for example, if you decide to like sell your iRobot to like your neighbor, and your neighbor is like this techie who likes opening up things and then looking at like memory.
Yeah.
That behavior problems.
Yeah.
As long as there's something that like a button that deletes the memory,
Yeah.
or you like give it to someone else, I think.
Yeah. Go ahead.
A good point about memory. If I let loose a Roomba in my home,
Yeah.
is it going to remember what my home looks like forever?
Ah.
So like I hit it with a hammer.
So I don't, I don't know for sure. I think the answer is yes. I don't think it deletes. I guess if it did delete the map, it's just going to build up another map, right?
If it did delete the history every time, it would be less efficient, but that might also help, because then you would, after you hit your house, you would, okay, new Roomba.
Yeah, new Roomba, like new map. But like, how do we know, right? Does someone know like whether that information is being, like someone maybe who owns a Roomba, like do you know if that information is being shared? Go ahead.
I don't know. I was just gonna say, like, with like smart technology, a lot of it is starting to become like Wi-Fi and cloud-based. So
Yeah.
I imagine like maybe you want your Roomba like synced up with like your, I don't know, like something like your Alexa. I don't know why
Yeah.
you would want to do that, but then it'd be like on Wi-Fi. So like, what if someone like hacked into your like Roomba or something?
Yeah.
Roombas do remember.
Do you remember? Okay. All right. Nice. Go ahead at the back, and then.
I know iRobot was bought by Amazon recently.
Yeah.
So
that would be a reason to connect it with Alexa. Yeah.
so now you have like Alexa, yeah, all the audio,
Yeah.
all the space,
Yeah.
everything you like to buy,
Yeah.
like ads.
I feel like
That's
that's
pretty much.
You can also control
all you can get.
remotely from your phone too.
Okay.
What if somebody else gets your phone and then they're like, I'm just gonna clean their house?
Yeah. Or mess it up, right? Go ahead.
I know with like some of this technology, there's a push to like do a lot of computation on the edge.
Yeah.
So you don't have to like send a lot of data to like the cloud. So I guess that kind of like helps a bit with like privacy if everything is kind of like just localized.
Yeah, if the computation is like truly localized, and if we had like some way to verify that, right, then I think like that is one possible like technical answer. Like if the company just says, look, here's a proof that the robot is not sending much information, all the computation is like happening on the edge, like on the device, and maybe there's like little bits and pieces of information that are being shared, but not all of it. Like in some sense, there is an incentive to share like data to some like centralized like processing system, right? Like maybe there's some home that's like has a weird geometry and the Roomba like has trouble. That might be useful information, like to process that, fix the algorithm so that it doesn't make mistakes in a weird environment. So I feel like there's an incentive to share in some kind of centralized way, but good.
Just talking about how, like, there's also, you can deliver groceries via drone.
Yeah.
And if
Well, I guess not
it's-
yet, but
Not yet,
in
but
principle,
once-
yes, yeah.
And when it drops it off, you open your door, you collect your groceries.
Yeah.
And that robot is building a map, and it'll include a map of what it sees on the inside.
Sure. Yeah. Yeah. Thoughts?
I think with Roomba, I think it makes an initial map of your home, and then each time it goes and cleans, it makes small updates to that map,
Right.
depending on if it like ran into stuff earlier and things like that. So
Yeah.
it's like continuously updating the map that way.
Yeah.
But yeah, I think it saves it. I know you can like view it on your phone, and like you have to connect it over Wi-Fi. and then-
Yeah. 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 It's kind of tricky. Go ahead.
I just remember thinking, like, when I read or when I saw them use the Amazon acquired iRobot, I was thinking, if anyone wants an iRobot, they should buy it now before Amazon starts producing its own. And I think, like, related to that, I think one potential solution is to work on, like, antitrust policies.
Okay.
So that, like, even if you are giving away your information, like, you're giving it away, like, piecemeal to competitors.
Yeah.
Who will, like, necessarily share that
Yeah.
with each other.
Yeah.
And I think
Yeah. Yeah, that's a good idea. Yeah, I guess in general, like the legislation and like policies around this are fairly like loose, and there's been like more and more of a push towards like thinking about these kinds of questions with like privacy and like fairness as well when we get to some of the machine learning techniques. But yeah, the point here, I guess, is just, I mean, not to come to any conclusions, but just to give you a sense for these societal questions, and yeah, maybe some of you will come up with policies somewhere down the line that will help us tackle some of these questions. I guess any other final thoughts or questions? All right, I'll see you next week.